Hi, and welcome to the video where we talk about the usefulness of Lewis dot structures and how we use them to predict things like polarity, intermolecular forces, and solubility. So with that being said, in the previous video we drew many of these Lewis dot structures, so I'm not going to go over how to draw them, but typically what we would start with is just a chemical formula. So for example, we would start off with something like CH2O, and you have to be able to go from the chemical formula to the Lewis dot structure following the Lewis dot structure rules. So if you need to review that, there's a separate video for that. So once you know how to draw the Lewis dot structures, let's talk about what it will tell you. The Lewis dot structure will tell you or show you how the atoms are connected. So for example, you see the carbons are connected to the hydrogen and the oxygen. It's not that the oxygen is connected to a hydrogen here. And what types of bonds you have. So you can see you have a double bond in here. And that's pretty much it. And that's super important because from the chemical formula, you know how the atoms are arranged. So that's great. But Lewis dot structures are limited because they're flat and real, so two-dimensional, and real molecules are three-dimensional. If you want to predict things like the polarity or intermolecular forces, you need to know the actual shape of the molecule. And so for that, we use a different set of rules, something called VSEPR, valence shell electron pair repulsion theory. And that helps us to predict the shape of the molecule. So the way that we do that, you've seen this chart before, is if you count the number of electron domains around the central atom. You use that to predict the electron domain geometry, which is helpful if you want to know something like hybridization. I'm not going to go into that in this video, but it's helpful for that. And it also helps you to know a little bit about the bond angles. Then you would determine the number of lone pairs, because when we're focusing on the molecular geometry or shape of the molecule, we need to ignore lone pairs. So the electron domains will include the lone pairs, but for the shape of the molecule, we need to ignore the lone pairs. So we need to know how many we need to ignore. And then once you have those two pieces of information, you can predict the molecular geometry or shape of the molecule. And this chart kind of summarized that. Now, electron domains, by the way, just to be clear, are the spaces occupied by electrons, whether they're in lone pairs or bond pairs, around the central or focus atom. So let's count the electron domains in these examples and then use the chart to predict the shapes. I already drew the shapes down for us so we can see, and then we can move on to predicting other things. So in the first example, again, we focus on the central atom, which is carbon. The number of electron domains here is 1, 2, 3. So again, it's the space occupied by bonds or lone pairs around the central atom. And notice that the double bond counted as 1 as well, because whether you have 1 bond here or 2 bonds here, that's the same space. So that space counts as 1. So 1, 2, 3. And there are no lone pairs. So based on that, we would know that if we look on the number of electron domains, we have 3 electron domains and no lone pairs, the shape will be trigonal planar. And so I drew that molecule in that fashion. So we have a trigonal planar shape. All right, let's look at the next example. Here we have, I think I'll use a different pen, maybe easier to see. So again, we focus on the central atom, and we count lone pairs that touching that central atom as well. So 1, 2, 3, 4. This one has 4 electron domains. And one of those electron domains is a lone pair. Now notice I didn't count the lone pairs in the terminal atoms, you just focused on the ones on the central atom. So let's use our chart here and see where that falls. If we have 4 electron domains, the EDG is tetrahedral, but with 1 lone pair, the actual shape was trigonal pyramidal. And that's how I drew that here. All right, in this case, we only have 2 atoms. So whenever you have 2 atoms, it'll always be linear. If you wanted to, you could count the number of electron domains around pick one of the atoms, since they're the same. 1, 2, that would be 2 electron domains, one of which is a lone pair. In this case, it really doesn't matter. You will only have a linear molecule. And I forgot to write the one above. This was trigonal pyramidal. Okay, so Whenever you have two atoms, it will always be linear, but you could, if you wanted to, count the number of electron domains and lone pairs, and once again, it will be linear no matter what. Two atoms always align. All right, now we have this structure here, HCN. So in this case, there are more than two atoms. Even though if you look at it, you probably could tell it looks like a line, probably looks linear, but we can go ahead and do it anyway. So again, we focus on the central atom, carbon. We have 1, 2 electron domains, and no lone pairs. And in this case, when you have 2 electron domains, and I put a dash here because whether you have 1 or 0, it'll only be linear. So 2 electron domains, no lone pairs, linear. Whenever you have 2 electron domains, it'll be linear. Whenever you have 2 atoms, it'll be linear. All right, let's look at our next example. SO3 2-. So here we have sulfite. Again, let's count our, so 1, double bonds count as 1, remember that. 1, 2, 3, 4 electron domains, one of which is a lone pair. So one of the lone domains was a lone pair. So that would fall under 4 electron domains. One of them is a lone pair, trigonal pyramidal. So it's the same as the one above, the NBR. So again, these are just the shapes of the molecule. Let's look at this next example. This one here, it's not on our chart, so we're actually going to just kind of skip it, but I'll tell you this actually has 1, 2, 3, 4, 5, 6 electron domains, 2 of which are a lone pair. And the shape here is called square planar. We're not going up to 6 electron domains, so but that's the shape for that one. And for this one, it has no central or focus atom. Well, it has no central atom, so you would have to choose one to focus on. You can focus on the one on the left, for example, and you would count that it has 4 electron domains and no lone pairs. And this would be, each of these individual carbons are tetrahedral. And I'll put a star there because they're for individual atoms, not the entire molecule. All right, so that's done. Once you have the shape of the molecule, you can then use that to predict the polarity. So let's talk about what polarity is. Polarity refers to whether a molecule is polar or non-polar. And polar molecules have a negative and positive end. So a good example of that, if you look at CO2, CO2 is made up of carbon and oxygen double bonds. And the carbon is the least electronegative, it's less electronegative than oxygen. And so what happens is, in the bond, the oxygen is really strong. If you picture it playing tug of war, oxygen is super strong in this tug of war. It's pulling the electrons in that bond towards it. So it's going to have a partial negative. And on both ends, where the oxygens are, it's partial negative, and where the carbon is, it's partial positive. These aren't actual positive or negative charges. This is just showing relative where the electron density is. So in this case, this would be considered nonpolar because it has 2 negative ends. It doesn't have a positive and a negative end. Another way of looking at it is, if you were to draw what are called bond dipoles, these blue arrows that point towards the more electronegative atom, these bond dipoles will cancel out because they're equally they're equal magnitude and going in opposite directions. They're arranged symmetrically. On the other hand, if you look at water, oxygen is the most electronegative, so it's going to have the partial negative, and the hydrogens are least electronegative, so it has partial positive. So this has a positive end where the hydrogens are and a negative end where the oxygen is. So this molecule is polar. Or if you look at the bond dipoles here where the oxygen that point towards the oxygen, these bond dipoles don't cancel out. And so because we have this is a polar molecule, we draw a dipole moment for the entire molecule, which is an atom pointing to the negative end of the entire molecule. So that's a quick review of what polar molecules are. And in order to figure this out, to figure out if a molecule is polar or nonpolar, you need to be able to draw the shape of the molecule, and that's why we did via CPR. So, for example, if I drew water in a linear fashion, so if I were just drawing the Lewis dot structure of water, and I happen to draw it this way, it may not be so clear that this is it's polar or nonpolar. Actually, this is not the best example, and probably a better example of showing something like that is if I drew something like this. This would look like it's nonpolar, but this is actually a polar molecule. All right, so let's go into, instead of drawing the dipoles, the bond dipoles, and things like that, of that nature, we talked about a couple of shortcuts, right? So the shortcut is if you have two atoms, diatomics, like this example here where there's just two atoms in total, you would calculate the change in electronegativity, or the difference in electronegativity between the atoms by subtracting their electronegativities. And you don't have to know the electronegativity values, those will be given to you. And if the electronegativity difference is less than 0.3, it's nonpolar. If it's between 0.3 and 1.9, or sometimes 2.0, it's polar. And if it's greater than that, it's ionic. So we talked about that before. So for something like this, if you look at these are the same atoms, so their difference in electronegativity will be 0. So this will clearly be nonpolar. If a molecule has more than two atoms, we can use a checklist. Now this is a shortcut, so shortcuts and tricks and stuff don't work for everything, and we'll see an example where this doesn't work. But for our purposes, for the molecules we need to know, it will work. So it's nonpolar if the terminal atoms are the same, or there are no lone pairs of central atom. You need to be able to check both of these in order for it to be considered nonpolar. Another thing is if you have a molecule that is a hydrocarbon, which just has carbon and hydrogen atoms only, these are always nonpolar. And this really is not a trick per se, this is a general rule. So anytime you see carbon and hydrogen, it's nonpolar. All right, so let's look at how we can predict the polarity. We'll do it with using the, for a couple of them I'll show you using the partial positive, partial negative symbols and bond dipoles, and then using the shortcut. So if we were to use the partial positive, partial negative, if I look in this molecule here in this carbon-oxygen bond, oxygen is the most electronegative, so I'll do a partial negative symbol near it. The carbon and the hydrogens, and actually I'll just focus on the terminal atoms here to make it less confusing. You can see here that it has a negative end of the molecule. If I were to draw the bond dipole here, you can see it points up like this. So this molecule has a negative and a positive end, and it has a bond dipole, so clearly this is polar. And so drawing it this way with this shape will help to see that more clearly. So that's why we learned via CPR. Now, what if I didn't want to do that, just want to use a checklist? So if I look at my checklist here, this molecule has more than two atoms, so I'm going to use this part of the checklist. It's nonpolar if the terminal atoms are the same. I can't check that. I can't even check that first box, so it's automatically polar. Remember, you have to check both of these to be nonpolar. All right, let's just use the checklist moving forward. So here we have NBr, and all the terminal atoms are the same, so that part I can check off. No lone pairs in central atom, I can't check that one off. So this one is also polar. In this case, this is a diatomic molecule. It just has two atoms, so I can't use this checklist. I'd have to go to calculating the differences in electronegativity. And in this example, the difference is, since they're the same atom, if I were to subtract electronegativities, it will be 0. So this is definitely nonpolar. Here we have a molecule with more than two atoms, so we'll go back to our checklist. All right, are the terminal atoms the same? No, they're different. So automatically this is polar. I couldn't check off any of these things here. Going back to this checklist, because it has three atoms here, terminal atoms are the same. Yes, they're all oxygen. No lone pair in the central atom. I do have a lone pair, so I can't check that one off. So this one is polar. Looks like we're not going to have any polar. All right, so here are the last two examples. I'm going to skip XeF4 and go to this one, and then I'll come back to XeF4. So in this case, we have more than two atoms, so we're going to use the checklist. But this is an example where we'd use the bottom part of the checklist, where it says all hydrocarbons. Carbon and hydrogen atoms only are nonpolar. All right, finally, let's go back to this one here. So this is an example where this shortcut of this checklist doesn't work. If we were to use this checklist, we would say, oh, all the terminal atoms are the same, no lone pairs in central atom. Oh, there are lone pairs in central atom. Well, clearly this is polar. This is actually nonpolar. And the reason, this is an example where the checklist doesn't work, but we don't have to worry about these because we're not doing things with electron domains of 6 or with 6 electron domains. But I just wanted to quickly point this out here. These bond dipoles would cancel out So you have a nonpolar molecule, and that's why the bond dipoles are helpful. If you were to draw the bond dipoles or the partial negative charges around, you would see that this is a nonpolar molecule. All right, so that is that. Now, why do we need to know the polarity? The polarity helps us to figure out the intermolecular force. Now, what are intermolecular forces? Intermolecular forces are forces between molecules that help you determine melting point, boiling point, surface tension. The stronger the intermolecular force, the higher the melting point and boiling point. So you can see the forces between. These are water molecules. All right, these are separate water molecules, and there are forces between them that are holding them together. If there were no forces holding molecules together, everything would be in a gaseous state. All right, but we don't. We have liquids and we have solids, so there must be something keeping those molecules close together. Now, for us, we need to know three main types of intermolecular forces. And the stronger the forces are, the higher the melting points and boiling points, etc. And we have the three we need to know arranged in order of strength. So the weakest one are London dispersion. Everything has London dispersion. But if it's a nonpolar molecule, it will only have London dispersion. If you have a polar molecule, in addition to London dispersion, it has dipole-dipole. So the dominant intermolecular force in polar molecules are dipole-dipoles. And finally, if you have a molecule that has hydrogen attached to an oxygen, attached to a fluorine, or attached to a nitrogen somewhere, anywhere in the molecule, then that molecule will undergo hydrogen bonding. And hydrogen bonding is the strongest. It's basically like an extreme form of dipole-dipole. So the purpose of knowing whether something is polar or nonpolar is so that we can predict these intermolecular forces, which then helps us to predict whether or not something has a higher or lower melting point or boiling point relative to something else. Remember, the stronger the intermolecular force, the higher the boiling point or melting point. So let's go ahead and take a look at this. All right, so let's look at this first example. We said it's polar, so we know it's either going to be dipole-dipole or hydrogen bonding. So let's just double check. For hydrogen bonding, we're looking to see if their hydrogen is attached directly to an oxygen, fluorine, or nitrogen. This molecule has an oxygen and it has a hydrogen, but that hydrogen is not directly attached to that oxygen. So this is just going to have dipole-dipole because it's polar. So I put DD for dipole-dipole. All right, let's look at the next example. Here we have NBr3, and once again, we see that it's polar, so we know it's either going to be hydrogen bonding or dipole-dipole. We look to, there has a nitrogen, but no hydrogen directly attached to it, so this is going to be dipole-dipole. So if the molecule was this, NH3, if it was this one, where the hydrogens are directly attached, then we would have hydrogen bonding. All right, but this one only has dipole-dipole because there's no hydrogen directly attached to the nitrogen. Okay, this molecule is nonpolar, so let's see what type of forces we have there. If it's nonpolar, the only forces available are London dispersion. I'll do LD for that. This molecule is polar, and once again we look at the molecule to see if they're hydrogen. So we know it's going to have dipole-dipole, but we'll check to see if it has hydrogen directly attached to oxygen, fluorine, and nitrogen. It has a hydrogen, but that's not attached to the nitrogen, it's attached to the carbon. So this one is just going to be dipole-dipole. Let's look at this example. We have a polar molecule, and there are no hydrogens here. So we automatically know we got ourselves a dipole-dipole. This one's nonpolar, so it's just going to be London dispersion. Remember, when there's nonpolar only, it's London dispersion. Okay, and last thing, the same thing with this one. This one just has London dispersion. Okay. So you use the polarity to figure out the intermolecular force. All right, last thing. The other thing you can use the polarity to do is to determine the solubility. So polarity can be used to figure out the intermolecular force, but also can be used to determine the solubility. So if a molecule is, there's something called a like-dissolved like rule. If a molecule is polar, it will likely dissolve in a polar solvent like water. And if it's nonpolar, it will dissolve in a nonpolar solvent like oil. So, for example, on this first one, it's polar. So we could predict that this will dissolve in water. Because it's a polar molecule. This next one is also polar, so we would also predict it's soluble in water. Now, it doesn't mean it will be, because their solubilities have to be comparable. Water is very polar, so if something is only slightly polar, it may not dissolve in water. But for our purposes, these are just predictions, so we're just predicting it based on the simplest thing. N2 is nonpolar, so this will dissolve in, it's insoluble in water, but it may be soluble in oil. Because oil is nonpolar. All right, next one. This one's polar, so you can guess it will be soluble in water. Same thing with this one. It's polar, so soluble in water. And then the last two examples are nonpolar, so they would be insoluble in water, do not dissolve in water. But soluble in oil. Alright, so I hope you found this video helpful. You can see how we can go from the Lewis dot structure to predicting the shapes of the molecules, which we then use to predict the polarity, although with the shortcut you can go straight from the Lewis dot structure to predicting the polarity. And once you predict the polarity, you can predict the intermolecular force and the solubility. So I hope you found this video helpful, and have a quality day.